Bismillahirrahmanirrahim. So continuing the discussion on the link state routing protocols, this slide illustrates the requirements or the main characteristics of the link state routing protocols. So in terms of memory requirements, typically link state routing protocols use more memory, and the reason for that is because each router needs to store the link state information of every single link in the entire network. So that's why the memory requirements is high in general for link state routing protocols. For the processing requirements, it's also high because link state routing protocols, they use a centralized algorithm, which is the Dijkstra algorithm, which again processes the link state information table to construct the shortest path tree. So for that we need we need CPU requirements, intensive CPU requirements for link state routing protocols. In terms of bandwidth requirements, well, the initial bandwidth is usually very high because the link state advertisement or the link state information needs to be broadcast and propagated in the entire network. But once you reach conversions or you reach synchronization between all the link state table of all the routers, then you switch to the trigger-based mode, to the trigger-based link state advertisement. So only during the initial phase, until you reach the conversions, the bandwidth requirements is high. The bandwidth requirements here is meant for exchanging the link state information versus exchanging, for example, the route updates in the case of EIGRP. So initially we are required to send, this is not periodic, we are required to send all link state information from each router to every single router in the network, and that requires a high bandwidth initially at the beginning. But after we reach conversions, we switch to trigger-based, which makes it a low in terms of bandwidth requirement. The main requirements for link state routing protocols in general. So with that said, we are going to discuss only one example of the link state routing protocols, which is a OSPF, or Open Shortest Path First protocol. So we're going to discuss OSPF only, which has been released in late 90s through the RFC 1247 and 2328. Not that this makes any difference for us, but historically the OSPF version 2 has been released in late 90s or mid 90s. They started the OSPF version 3, which supports IP version 6. So OSPF version 3 it was released to support mainly IP version 6. So the addressing scheme and the route updates and everything and the subnet mask and all of this is fundamentally different in the case of OSPF version 3. Okay, so digging into the specification of OSPF, and here we have to pay attention because there are some similarities conceptually between OSPF and especially EIGRP. Okay, there is some overlap because, as we said, EIGRP is not exactly a distant vector routing protocol. It's somewhere in the middle. So you will see that there is hello packets, there is request and reply and so on. However, there are slight differences that you need to pay attention to. Okay? So in terms of message encapsulation, you have normally the data link frame header. So the data link frame header will contain the MAC address, and the MAC address is usually multicast address, and we'll talk about why we use in general multicast address. And we have the IP header. So for the IP header, we use protocol ID 89 to indicate that the payload is going to have OSPF message format. So these are standard things, okay? And again, similar to EIGRP, we don't see any transport layer protocol, which means that OSPF uses its own transport layer protocol, right? Similar to EIGRP, unlike RIP, which uses UDP. Okay, so for the OSPF packet header, so we have OSPF packet header and the payload. The OSPF packet header simply shows the type code for the message type. So OSPF uses one of these 5 different message types. So you have hello message type, you have database description, which we will talk about. We have the link state request, which corresponds to route update in the case of EIGRP. You have link state update, and you have the link state acknowledgement. So you have again request and acknowledgement. Again, kind of similar, except that here we do that for the link state information, not for the route itself. Okay, and there is a big difference. So the message type here indicates one of these 5 types, which we will discuss in details in a minute. And then you have what we call a route ID, and you have the area ID. So the route ID is an identifier for the router itself. Okay. The area ID is a new concept that OSPF uses, which we will discuss in details. But just to give you a brief idea, the area ID is something which is included in OSPF to address the issue of scalability. Okay, so as we said before, the autonomous system is a group of routers that are governed or controlled by a single authority, right? So if you have a very large autonomous system and you have to propagate the link state information to the entire autonomous system, the overhead is very large. Okay, and that leads to very large, again as we said, very large memory requirements, very large processing power in order to process the link state table and so on and so forth. Right? So, so to mitigate this issue, they have divided logically the autonomous system into a group of areas, group of sub areas. So you will see that. So it's like you have an autonomous system, which is a big autonomous system like this. You have group of routers. Okay, and inside this autonomous system, you have areas. So you have one area here, and you have one area here, and you have one area here. Okay, so the autonomous system itself is divided logically into areas. The reason for this is to again control the broadcast domain when it comes to exchanging the link state information. So this way, the link state information is going to be exchanged within those three domains. And the link state table is going to be limited in terms of memory requirements and as a result in terms of CPU requirements and so on. Okay? So that's the message format for OSPF, and from now on we'll talk in details about the packet header and each of these messages in more. So first, this is like a brief list for the types of messages and the definition or the purpose of each one. So you have the hello packet, and we all know the hello packet, except that hello packet for OSPF has more function or more purposes compared to EIGRP. Not to just discover adjacencies only. It is to discover adjacencies, but it's used to also do something else, which we will talk about. Database description, and this is a totally new message type. Okay, so database description, it used to check the database synchronization between routers. So what happens is that a router will actually group the link state information from its link state table in a very abbreviated form. Okay, you know, like similar to when you receive your email from IMAP server or something, you receive like just very simple headers, and the headers are going to be grouped in like a payload and sent to you. And then if you are interested in a mail, then you get the details of the mail. So same concept. So the database description here is used to for a router to send its own information to another router, and this router will check whether the link state information in the neighboring router synchronizes with its own link state information. Okay? So this message is used for database synchronization. And the reason is that we need some mechanism to allow us to reach conversions. Conversions, for the case of link state routing protocols, as we said, conversions is when we have a synchronized link state table between the routers. Synchronized link state table. They have to be identical, right? Because each router needs to have separate link state information for every single link in the entire network. Right? So unlike EIGRP, there's no something called link state table. But here the synchronization happens if all the routers have the same link state information. Okay, so pay attention to this carefully. So in order for us to check whether we have a synchronization state between the link state table, we use what we call a database description message. So the rest is kind of standard, except that we don't do it for routes, we do it for link state information. So what we exchange between the routers is actually the link state information, not routes. So here we have link state requests. So a router, based on whether it finds that its own table is synchronized with others or not, if it finds that there are some missing entries in the table, for example, as we said, a neighboring router sends to you that he has let's say like 30 different link state information, okay, and he gives you like very simple headers of each one of them in one message, okay. Then you compare this with what you have, you find that you have like 25 and there are 5 missing. Okay, so in that case, you send a link state request requesting that I need the information for those 5 missing links. So this link state request is going to propagate to the neighboring routers, and then the neighboring routers will send you the details about these missing 5 link state information. They send it to you in a form of link state update. So you send a request, okay, you get the update, and then you send the acknowledgement. Okay, so that's how it happens. Of course, the link state update can be triggered by network change. So it doesn't have to be based on a request. Okay, so the link state update can happen due to a request, or it can happen due to a trigger-based change. So if one network goes down, if one link goes down, if another router gets connected and stuff like that, then you recognize this as a new change in the network. In this case, you send a triggered update with in a form of link state update packet. Okay? Any questions? So let's go to the details of each of these messages. So the first one is the hello packet, and as we said, the hello packet has the main purpose of the hello packet is also to discover adjacencies. So similar to EIGRP, you need to discover the neighbors. Why? Because if you don't have any neighbors, you don't have to send any link state information, right? If you don't have any neighbors, then you don't have to send anything on the links. Because remember, you may have some routers connected to you, but they are not neighbors. So when does that happen? If these routers do not use the same routing protocols that you do. Okay? So even though you have some connected routers physically, they are physically connected, but logically these are not neighbors because they are not using the same routing protocols that you have. Okay? So with that said, the main purpose of the hello packet is to discover the adjacencies, and the adjacencies here are routers that use the same routing protocols, and they advertise guidelines on which routers must agree to become neighbors, and that's very important. For this part does not exist in EIGRP. So in EIGRP, we agree only on the autonomous system number. If you remember the autonomous system number, or what we have called it the process ID, then they have to agree that the process ID is the same and the routing protocol is the same, in which case they are neighbors. That's it. Here, we have to agree on certain information. We have to synchronize this information between us. So you have, so in the hello packet, you have the packet header, and in the packet header you have the message type. And let me just try to maximize it a little bit. So you have the type. Here the type is 1 to indicate hello packet, right? So this is the message header. You have the router ID and the area ID where this packet is originated from. So it's originated from a specific router ID in a specific area. The main reason for the area here is that if you have to propagate this message further, then you have to have your limit to be the area. So it should not go outside of the area. Okay? So and you have some checksum and authentication which are used for security and as transport layer address exchange. And for the hello packet itself, you have the network mask, and you have the hello interval, and these are the values that you need to agree on. You have to agree on the hello interval, the router priority, the router dead interval, designated router, backup designated router, and the list of neighbors. So you have to agree between you and your neighbor about these values. So the hello interval itself, as we said before, the hello interval is used to specify the frequency that you use to send hello packets. So that's easy. What you need to agree on specifically is the router priority, is the designated router and backup designated routers. Those did not exist before in EIGRP. Okay, we'll talk about them in details in the following slides. So the router priority indicates the priority of how to trust the information coming from this router. If the router priority specified for one router is the highest, then this router is highlighted as the designated router, and the next priority will be the backup designated router, and we'll talk about the purpose of those two entities. So between you and your neighbors, you have to agree on these things, because we'll see later on that these designated routers, they have very special function that without which the network will not function properly. So that's one of the main purposes of the hello packet is to agree on the priority and the designated routers. As we will see in a minute, the hello interval for OSPF, it uses similar concept like EIGRP, but the default values are different. So you have to pay attention to this. Also the router dead interval. The router dead interval is what we used to call for EIGRPA. The one you will not remember. We used to call it the whole time, and the whole time is the parameter that specifies the duration after which you consider your neighbor A dead. So if you don't receive any hello packet within that duration, you consider your neighbor dead, and the link is off. Okay. So I think that's all. So the hello packet is also used by multi-access networks to elect a designated router and backup designated router. So that's what we have mentioned, and this is a very important feature which did not exist before in the case of EIGRP. So that's one extra purpose for the hello packets, other than just to discover neighbors. Any questions so far? This is the first message type, which is the hello packet. In terms of parameters, in terms of values for these parameters, the hello packets they contain the router ID, as we said, the router ID, the originating router, and the originating area. The interval, the hello interval, usually is sent in a form of multicast. Why not broadcast?
Because it's bounded to a specific area. Because it's bounded to a specific area.
No, because not every single physically connected router is by default a neighbor. And remember that multicast is the general form of transmission. Broadcast is a special case of multicast. So just the fact that you use this address, it doesn't mean that you cannot broadcast to all neighbors. You can broadcast to all neighbors, but this address indicates group of routers. Okay, so these routers, if this group contains all the physically connected routers, then this is technically a broadcast. But this is not the general case. The general case is that you have some physically connected routers which are not necessarily neighbors. In which case, not all of them will be targeted by the hello interval. Remember that. Okay, so you have three values here which are different from EIGRP, and you need to pay attention to this. If you remember, the hello interval for EIGRP used to be 5 for the point-to-point links, and point-to-point links are these type of links. So this is point-to-point. This is point-to-point. This is point-to-point. This link, we call it broadcast multi-access. Okay? Why? Because you send one packet and it reaches all of them, because this is shared. Okay? So for those two types of links, whether it's point-to-point or broadcast multi-access, the interval for the hello packets for the case of OSPF is 10, not 5. Okay? For the case of non-broadcast, multi-access, the interval is 30. So what is that non-broad? How come it's multi-access but it's not broadcast? So we discussed that before in the case of EIGRP, and what happens is that if you have 4 routers like this, and you have in the middle, you have a switch. So you have router 1, 2, 3, 4. If so those routers are connected to the switch like this. Okay? This is an example of a network that we call it multi-access. Why is multi-access? Because all routers are connected to a switch. So multi-access means that you can send messages from here and here, and the switch will resolve the multi-access issue. Okay? But it's non-broadcast. Because the broadcast example is something like this. If you have a network like this, and you have routers like this. This is multi-access, but it's broadcast network. Why? Because if one sends one packet, it gets shared by all of them. Okay, so this is multicast and multi-access and broadcast network. This is non-broadcast multi-access network. And there are so many examples, like frame relay uses this type of physical topology. If you have like even Ethernet, if you have Ethernet with a switch and you have multiple routers connected to a switch, again, that's a type of non-broadcast multi-access network. So in this type of networks, the hello interval is 30 seconds, not 10 seconds. The reason for that is that, again, as we said, the hello packets and the link state information, it gets sent in a form of multicast in general and broadcast to all the neighboring routers. So for this case, for the case of broadcast, you send one hello packet and it reaches all of them, right? In this case, however, each router needs to send multiple numbers of the message to all the neighboring routers. Why? Because the message has to go this way and it has to be replicated. Right? So if you want to send broadcast, because the switch will not broadcast it for you, you have to send to all the neighbors. So each router will have to send 3 copies of the same message. Right? Because this is physically non-broadcast network. So in order to facilitate the broadcast of the message on a non-broadcast network, then you have to send multiple copies of the same message. So each individual router will send multiple copies of the same message in order to flood the link state information. Whether this happens in the case of hello, and this happens in the case of link state. Right? Both should be propagated to all the routers. This initiates a huge amount of messages and duplicate messages on the network, and especially on the switch. Right? Because each router will have to send 3 copies of the message. 3 copies, 3 copies, 3 copies. All of them will have to be resolved by the switch. This initiates a huge amount of overhead, especially on the switch. That's why we need to mitigate this by reducing the frequency of the hello packets. Okay? So this will solve the problem for the hello packets, because the hello packets are periodic, right? So by controlling the period of the hello packets, you can mitigate this situation. So reduce, instead of using 10, use 30. Right? So what about the link state? Because link state is not periodic. How do we control that? Because this, again, for link state advertisement, this again will generate a huge amount of traffic on the switch. So that's the main reason for using what we call a designated router and backup designated router. And we'll talk about the details of this later. But the concept has to be very clear for everyone. Okay? So this is what we call a non-broadcast multi-access network. So these are physically star topology. However, we have to deal with it as a broadcast domain, in which case you need to do extra overhead of duplicating every single message multiple times to reach to all neighbors. So that's why you need to have some way of reducing the traffic for this special type of networks. Any questions? Okay, so to go back, we have the hello interval, which again is 10 for the case of point-to-point. Why? For the case of point-to-point, we don't have to it's like two routers simply connected on one link. So there is no issue with that. Again, for broadcast networks, it's a shared line, so you send one copy of the message and it gets broadcast to everyone, right? So again, there's no issue here. So the hello interval for those two types of networks could be high, which is in that case it's 10. In the case of EIGRP, it's 5. The dead interval, which used to be called hold time, here is 4 hello packet duration. 4, not 3. In the case of EIGRP, I'm relating this to EIGRP just to give you the slight differences. So the dead interval here, which used to be called the hold time, is here 4 times the hello duration. So for the case of, again, point-to-point, the dead interval is 40 seconds. For the case of non-broadcast multi-access network, the duration for the dead interval is 120, bro. So 120 seconds. So if I don't receive any message within that duration, I consider the neighbor, he is not neighbor anymore. As we said, the hello protocols, they contain information that's used in electing the designated router and non-designated router. So what happens is that, again, in a special type networks like the one that we talked about, the non-broadcast multi-access network, again, the traffic will be huge, especially for link state information which gets flooded to all the neighbors. So if we don't do anything special to mitigate this situation, the bandwidth requirement will be very, very, very high. So to mitigate that situation, instead of allowing each router to broadcast to all neighbors, we'll not do that. Okay? The hello protocol will be used to elect one, again, amongst the so if we go back to the example that we talked about, so we have, again, 4 routers like this, and so we have 4 routers and we have a switch in the middle. So instead of having each one sends to all the 3, no, we'll not do that. We'll designate one of these routers to be called the designated router. Okay? And then, instead of all the routers sent to all routers, no. Each router will have to send one message only to the designated router. And the designated router will forward it to the other routers, except the one it came from, of course. So this way we can reduce the traffic drastically, right? So this is the main concept of designated router and a backup designated router. So there are some issues with that, and that's why EIGRP did not bother using this. Okay, there are some issues with that. The first one is that who is going to be the designated router? So we need some election process. So at the beginning, we need some election process. And this is one of the functions of the hello protocol. So the hello protocol is used to elect who is going to be the designated router. So this is the first issue. So the first issue is the election process, and we resolved that using the hello protocol. The second issue is that by designating one router, okay, if that router goes down, then the entire network is non-functional, right? So you are essentially creating some kind of a bottleneck in this type of network. So if this router for any reason goes down, then you're doomed. Okay, so what do? We highlight what we call a backup designated router. So the backup designated router is used to overtake the functionality of the designated router in case the designated router goes down. So those are the two main issues, and this is how we solve these issues. Okay, so any question here? So that's what's described in this part here. So the second part. So we now, by this time now we have exchanged the hello packets. We have identified all the neighbors. We have the neighbors specified, all the adjacencies specified. So now we can exchange the link state information. So at this time we can exchange the link state information. So there are multiple types of the link state information here, which we don't have to get to. These are detailed types for specific, for different situations, and these are actually discussed in CCMP, so we don't have to bother about this. However, we need to understand that the link state advertisement and the link state update, these are two terminology for the same thing. The link state advertisement is sent as part of a link state update packet to all the routers in the area. And these contain, again, the cost, which is, in that case, the bandwidth of the link and the description of the link. Okay? And these are exchanged in two cases. The link state update is sent as a result of receiving a request. So if you receive a request about a specific link state information, you send it in a form of link state update. Or you don't receive a request, but there is a network change that happens. In that case, you trigger a link state update. You want to inform all your neighbors about this new change that happens in the network. Okay, so those are the two. So this summarizes the logical steps that OSPF takes to form the routing table. So again, remember that our ultimate objective is to form a routing table. But here, a prerequisite step that we have to do is to form the link state information. We put it in the link state table. We make sure it's synchronized with all the other routers, and then we run the Dijkstra algorithm or the OSPF algorithm. We run it once against the link state table. Okay, we form the shortest path first tree. So you run it from one router, and this router will generate the tree, which illustrates, if I want to go to this destination, how can I go? If I want to go to this destination, how can I go? And so on. So you form a tree, the root of which is this router. And from this tree, you form the routing table. So those are the logical steps that OSPF takes. Okay? Of course, this is quite similar to EIGRP. OSPF again uses authentication, and as we illustrated and as we discussed in the OSPF packet header, we have authentication information that has to be exchanged between the routers, and this includes certificates and so on, which facilitate the authentication between the different routers. So again, the main purpose of the authentication is to make sure that the routers that are sending information to you are really authorized and they are identifiable routers, not like attacker or someone who is trying to attack the network. So that's the main purpose of so again, similar to EIGRP, we use the router command to specify or to trigger the use of OSPF. So we say router OSPF, and here we call it a process ID. Again, pay attention to these slight differences. In EIGRP, this is called the autonomous system number, but it actually indicates a process ID. Another main difference here that you need to pay attention to is that for OSPF, any router in the area that uses OSPF is considered a neighbor to you. Okay? For the case of EIGRP, if you remember, the router that uses the same autonomous system number is the one that may be considered a neighbor to you. So that's again a minor difference. So for example, if you specify router OSPF 1 on router 1, 2, 3, those are technically will start exchanging information and they will consider themselves neighbors to each other. However, even if you say here OSPF 1, OSPF 2, OSPF 3, these are still considered neighbors. Okay, so the process ID itself does not mean that OSPF process will not exchange information with another OSPF process with different process ID. This is unlike EIGRP. The reason for this is that the area ID is what we use to distinguish between the different OSPF areas. So we don't actually need different process IDs to indicate different logical processes for OSPF. So for OSPF, the area ID is the main issue or the main parameter that we use to limit the neighbors in the area. So that's why it's mentioned here that this is a locally significant. It's a locally significant number. It doesn't mean anything globally. For EIGRP, it does. It does mean something globally. Autonomous system number, it does mean something globally, because if two routers are running EIGRP with different autonomous system numbers, these are not neighbors. But here, the number is locally significant. It doesn't mean anything globally. What means something globally is the router ID and the area ID. And these are exchanged as part of the packet header as we discussed. So the router ID means something and the area ID means something. And that's very important. But we don't actually, the process ID, we don't exchange it between the routers to indicate anything. Okay? So the hello packet exchanged back and forth will not actually contain any information about the process ID, in which case two OSPF processes with different process IDs will still be considered neighbors. The last thing for today is the OSPF metric. The OSPF metric is what we call the cost, and if you want to calculate the best route for a specific destination, you compare between all the potential routes based on the cost. So the path that has the lowest cost is considered for you the best path or the best route. For EIGRP, we used 4 different parameters to combined to form the metric or the cost, right? The bandwidth, delay, reliability, and load, right? For this case, we're using only one parameter, which is the bandwidth. And again, the bandwidth here is an offline bandwidth. The offline bandwidth, which is specified based on the characteristics of the link. For example, if you have point-to-point T1 connection, the bandwidth by default is 1.544 megabits per second. That's the bandwidth. Okay? It's not the running bandwidth. It's not the real-time bandwidth. Again, similar to EIGRP. Okay? Another slight difference here is that the cost is calculated based on the reference bandwidth. In EIGRP, the reference bandwidth, of course, no one will remember that. The reference bandwidth used to be 10 to the power 7. Here is 10 to the power 8. Okay? So the reference bandwidth here is 10 to the power 8 divided by the bandwidth of the link. So if I want to calculate, for example, the cost for a T1 link, so it's simply 10 to the power 8 divided by 1544. As simple as that. So that's the cost. So this is simply the cost. And the cost here for Ethernet is 1, because the bandwidth for 100 megabits per second is again 10 to the power 8, so the cost is 1. So 10 to the power 8 divided by 10 to the power 8 is 1. And similarly, you can calculate the initial cost for every single link based on the type of this link, whether it's T1 connection, it's serial point-to-point, and so on. Okay, any questions so far? There is another difference that we will talk about next time, which is again very, very important. So